Okay, this question. Right. So this is still not the PWM question that I want you to find. So someone find a PWM question of the kind that you were talking about, where the counter gets loaded. It's a loadable counter. So it doesn't count from, for example, 0 to 7 or 0 to 15. It gets interrupted and counts to some other number. And then there's a PWM associated with that. So someone raise their hands. Yes? Did you find one? Say louder, please. 47C. Okay. Okay, maybe we'll do that. I think there are better examples, which maybe I have to find. But let's do this one first. So, okay, this is another question where you're asked to fill in the timing diagram for consecutive clock pulses. Right, it looks like that. What components do we have here? We have an up counter and a down counter, and we have a mux. And each of the counters can be loaded when their respective load signals go high, and they'll be loaded with zeros in both cases. Okay, so the inputs when the loads go high are zeros. Oh, we've also got a D flip-flop right here. And then we've also got an input X, which is the selector to the mux. So there's quite a few different things going on here. What's given to us is LP, the load signal to the down counter. That's given to us for the entire time sequence. And X is also given to us over that period of time. So the first thing to do, and it's been conveniently arranged in sort of the right order to approach the question, is to find out what LQ is, right? So LQ is the output of the D flip-flop fed by LP. So that should be straightforward because the D flip-flop, it's called a D flip-flop because it delay flip-flop. Every clock period, it will put into LQ what it just saw in LP, right? So it takes that 0, puts it in there, and that 1, and so on. Okay, so it just delays LP by 1 clock period. So we can ignore X for the moment because we're not at the mux, but we can investigate what P01 is P0 and P1 are doing. So P0 and P1 are the outputs of the down counter. They started off at 0, 0. And so one of two things can happen, right? You can either count down from your previous value, or if the load signal was high, it gets replaced, it gets loaded in with 0, 0. Okay, so for time 1, we have to look, we were at the value 0, 0. Do we load or not? So we look at the previous value, the time 0 value of LP, which is 0. Right? So it's actually this value that feeds in and determines whether we load or not. Since it was 0, the load is low, so we count down. So counting down from 0 gives us 1, 1. It gives us 3. It gives us 1, 1. Okay, I should have done 1, 1 from the bottom up. Right? We can go to the next stage now. At the next stage, our load signal was just equal to 1, and so we don't count down. We replace our value with 0, 0. Right? For the next one, we do count down because the load is 0. So we count down from 0 to 3, and then the same is true. We count down from 3 to 2, 1, 0. Okay, that's the top part of it. So this is a loadable counter. The important thing is that the load signal to use is the one before the clock cycle to propagate after the clock cycle, right? To propagate the output after the clock cycle. Q0 is Q0 and Q1 are very similar, except they are the outputs of an up counter. And we're now looking at LQ, and when LQ is high, we reset to 0, 0. So I cannot fit that on the page, but let's remember those rules. So in this case, starting at the value 2, this is 2, so this is 1, 0. We count up because LQ is 0. Count up to 3, 1, 1. And then LQ is 0 again, so we count up from 3 to 0, 0, 0. At this point, LQ goes high, so we don't count up, we just feed in the values of the inputs, which, if you remember, were 0, 0. So we get 0, 0. And then in the next stage, we count up 0, 1 to the value 1. Okay, so I think those were the harder parts of that question. We can finish it off.
Why does Q1 start at 1? Is that just random?
Right here, why does it start at 1? That was just the initialization, right? These are memory circuits, so in order to analyze them, you have to know what they started off at. It could have been any, it could have been 0 just as well. Yes.
So when your load is 1, you just take the value which was given in the input?
Yes.
Otherwise you count down.
In a down counter, that's exactly right. When the load is 0, you count down. When the load is 1, you load in the
so
new value.
4 you count it to 3 and 2, 1, 0, again 4, 3, 2, 1.
Right, almost, but in a 2-bit counter, you cannot represent 4. So it's 3, 2, 1, 0, 3, 2, 1, 0. Yes. All right, so the final part of the question involves this mux. So the output F0, F1 is either equal to Q0, Q1, or P0, P1, depending on the value of the select signal, X. So if X is equal to 0, you feed in the Qs. If X is equal to 1, you feed in the Ps. And the X signal is given, right? So this is pretty easy. When the X is equal to 0, in these 3 cases, we just copy the Qs, right? We copy the Qs into the Fs. So there we copy the Qs, 0, 1, 0, 0, and 1, 0. And in every other position, X is equal to 1, so we copy the Ps, 1, 1, 1, 1. Okay, so that's how the multiplexer is working. It selects some of the inputs to go to the outputs based on the select value. Yes?
For the load signal, why do you look at the one with the previous?
Okay. So yeah, that's the critical part of this question. Why do you look at the previous load signal? Right? Why don't you look at the current load signal? For example, right here, when I wrote down P right here, I said we count down because the load is low, right? Why didn't I use this load being high and decide to reload the counter? This is basically because time goes forward, right? The past can only affect the future. So remember, everything in a circuit with a clock, all useful sequential circuits have clocks, and things only change at the clock's rising edge, right? So every decision is made at that instant. So at that very instant, this decision here is being made, this P0, P1. But this value of LP right here does not exist at that instant. That hasn't happened yet, right? So when you're dealing with a clock input, you have to at the previous interval. This is a bit different to the multiplex.